Okay, awesome. Thanks for having me, Matt. Glad to be here. Glad to talk a little bit about hardware security. As Matt said, I spend a lot of my time doing hardware security training, but I generally train software security people on kind of the low-level hardware, learning how to find JTAG, UART, SPY. Um, but my background, I worked at Intel for many years, and while I was there, I worked on silicon debug, speed path debug of desktop server CPUs, DFX, using DFX to do that stuff. So I've seen a lot of the insides of the hardware before going on into the security side of product security at Intel, before going out on my own and teaching hardware security to the infosec community that like thinks that, oh, it's hardware, it must be solid, it must be trustworthy, it must be it must work. We all know the case that beneath the full stack that they talk about is the full stack that we deal with, the hardware down to the silicon with the IP blocks and everything. So I just wanted to clarify, you may think I was going to go through 101 ways to flip bits. It's actually, in case you want to worry, this is the 20-minute version. This is the 101 ways to flip bits and 101 ways to stop it. And when I talk about flipping bits, I basically, you take 101, you flip it, and you get 010. So that's the kind of bit flipping we're talking about. There is a longer 2-day version, the, hex 101. Perhaps there's the signed binary, but we don't know how that's going to turn out. More importantly, I was really excited because just last week, the 2021 CW Common Weakness Enumeration vulnerability list weakness list was posted by MITRE. So what they've done is they've gone through and they've taken tons of these common hardware weaknesses and kind of given them code names, right? This is not specific bugs. That's the common vulnerabilities you might hear about. This is the common weaknesses. Like a lot of bugs seem to fall into this category. And these are the top 10 hardware weaknesses for 2021. So you should all read this list and become pretty familiar with it. But what really is important to me is the fact that I'm writing in white. Let me change my color to write in red so you actually see it. So right here, improper prevention of lock bit modification, right? So I'm talking about flipping bits, not just any bits. I'm talking about flipping lock bits and the bits that they're supposed to be locking. So what does that mean? There's some details on each of these, along with some examples for many of them. So the product uses a trusted lock bit for restricting access to registers, address regions, or other resources, but the product does not prevent the value of the lock bit from being modified after it has been set. So this sounds like a bad idea. Here's an example. Actually, I was just going to point out, that's the one I'm choosing, but there's a lot of other references to lock bits in these top 10 and even other common weaknesses. So I'll go through a few of those. So what's a lock bit? It locks other registers when it's set. So we have this critical register that's something important. Maybe it's the power supply setting or, something, a key that gets used. And you want, once this is set, you never want it to be changed. You don't want like end users, less privileged software, anything to go and modify this after the boot up and initialization has happened. Whether the initialization happens from like mask ROM, ucode, microcode, anything like that, or even user code. This is basically setting up a situation to be a known context that is executing. So we have a lock critical register bit, and we just set that to true. Now, once we've set lock critical register, right, we go and we try and change it, try to hack the value, and it doesn't work, right, because that register is suddenly locked, okay? Seems like that should be sufficient, right? But, hackers are creative, so we'll go and try this. Okay, so that first attempt doesn't work, but what happens when we just go ahead and we change that register to false, right? That lock critical register, if we change it, we can suddenly modify the register below again. So like we got to do a little bit more than this. We need to actually lock the register that we're locking with. We need to make it somehow secure. So once we've locked it down, it doesn't get unlocked. Again, my experience was at Intel, and the convention there was like basically reset. Like everything gets locked and set until reset. When the system resets, it has to happen again anyway, so it's all cleared. Depending on your target, your ASIC, your architecture, your design decisions, that might not be the case. You may have operating modes where certain things get reset or not, but that's mine. My assumption I'm going to go with. So what we do is we have what's called a write once lock bit, okay? And this is great because we set our value, we set our lock register, our write once critical lock register, and when we try and change the value of the critical register, it doesn't change because our lock register is locked. right? If we try and change the value of the lock register itself, it doesn't change because it's also locked. It's a write once register. Once it's been written once it has a value, it doesn't change. And so when we go and try to modify that register again, we can't do it. So we've been defeated as an attacker trying to maliciously change registers. However, there's a CWE for that, right? Improper prevention of lock bit modification. So if the product uses a trusted lock bit for restricting address or other things, but does not prevent the value from the lock bit from being modified after it's set. That's what we talked about before. But actually, let me go into a little detail here, an example. So this is one of the published examples, which is great because I know some examples I probably shouldn't talk about, but when they're on MITRE's website, I can talk about them, right? So we have this this temp sensor lock register, right? And we can lock it. And then we have this hardware shutdown register, which enables hardware shutdown on critical temperature detection, right? However, anybody can enable or disable this despite the fact that the sensor is supposed to be even locked. So the vulnerability, we basically need to make sure we lock the relevant register. So making sure you're locking the relevant things is pretty important. But even if we went so far as went to set it to this write one once situation, write once saturation, right? If we can sneak in ahead of time, like on a PC, if this is what the operating system does and we do this in the BIOS, right, or something like that, what if we go and we change our critical lock register to false, right? Now, that means it's a write once. We wrote a 0 to it. And now critical register is not locked, right? And then we later on go and write true to it, okay? The problem is it was written once already. It took the first value, it keeps the first value, it doesn't change that. That's a bad thing because we can then go and change it again and then try and fix it and then change it again. Over and over again, we can just modify the register because we've locked it open. Again, there may be cases when you want this to be possible, when you want to basically set up a system to not be locked down or unlocked permanently. But typically, this is not the behavior you want. So what we usually have is basically a write one once, right? So you can write a 1 to it one time. And so if you write 0 to it, it doesn't matter, right? If we did that before we write equal to 0, it doesn't matter. It's not a 1, so it's not locked. So basically, the lock register locks itself. Here we go. We write to 1. We can't change it. We write it to 0 again. It's already been written 1 once, so it stays 1, and it's good. Okay? But then, of course, we got to figure out a way to bypass it, right? The reality is we don't always write discrete values to registers. Oftentimes, we've got this lock setting register, and that lock setting might be a combination of logic that combines, a bunch of stuff with logic from different paths and chains. So it may not be a direct literal value that we're setting things to. So if we can influence the value of lock setting, right, then we can go and not let this lock actually happen, right? And so when we change it to false, it doesn't actually matter because we still have access to that register. So there's a CWE for that, right? The hardware design control register sticky bits or write once bit fields are improperly implemented such that they can be reprogrammed by software. So software or other combinational logic. And here's an example of a problem and a fix, right? Over here, we get down to this spot, right? Where we basically have that data in. That's the write once status that we set it to. And the solution is basically to say, nope, we're just writing it to a 1. So basically, anytime you write to this register, you're locking it, okay? So it doesn't matter whether you write a 1 or a 0. If you write to this register, you're locking it, which kind of removes that complexity, right? So we've got this improved write one once bit, right? It locks other registers and itself when it's written. It doesn't care what the data is written to it. So the critical register, we set a value, right? We set our lock setting. It doesn't matter what this value is because it's a write one, set when lock, set when written. And of course, there's no change. We can do as many more writes to it as we want. It doesn't matter. There's going to be no change because once it's been written once, it's set, it's locked. That's it. Doesn't matter the value you write to it. It's locked. So we got this improved write one once lock bit. But then we got to think like, okay, we talked about what really is that lock bit. Is it combinational logic or something? But what really unlocks the target register? Is there anything left that can still unlock it? A lot of times you have debug modes that do exactly that, right? Luckily, of course, there's a CWE for that. Let's see. Number 1, 2, 3, 4. Hardware internal or debug modes allow override of locks. Okay, so basically we've got debug modes that are going to give us some combinational logic that say, okay, So if write and lock status and scan mode and debug unlocked, right? So we have this combination of logic in there. And it basically says, oh, if you are a debugger, if you have your debugger attached, if you're in JTAG mode, if you unlocked JTAG or any of these like scenarios, then suddenly your locked register is unlocked. This might be necessary for hardware development and design and getting things up and running, but it's probably not the behavior you want typically. So how do we lock down the debug access? The typical answer is we authenticate the debugger. And authenticate can be a loaded word. It could mean that we do this cryptographically, right? It could mean that we have a key system, a device-specific key. We need to generate, all that fancy stuff. That's hard. That's complicated, but that might be what our product requires. It could just mean physical access, right? So this is the difference when we say things. We say, okay, we make no effort to protect against attacker with physical access, right? If we make that statement as a hardware designer and pass that on to the software users of our device or hardware users of device, that's good information. They'll know not to put trust into this thing. If, however, on the other side, we make a marketing statement that says, oh, your keys are safe in our chip, right? We're making some pretty strong statements about physical access without even saying the word physical access. We're saying that, oh, you can take this chip, you could put keys in it, and no one's going to be able to get them out. You don't explicitly say that, but that assumption is loaded in there with that statement. Okay, so locking down debug access, how do we get around that? Well, there's a CVE for that too, right? CWE 1191 on chip debug and test interface with improper access control. How are we gonna lock down debug interfaces? We'll use lock bits, right? So we're kind of going around in a circle where we have a resource we want to secure, right? We have a control bit that we can use to secure it. And then we have all the ways we can actually influence that control bit. And then all the ways we can influence the access to it. So here are my recommendations, right? This is a security detail, right? When you're getting your first chip working, like this isn't your priority. But if you're going to get to the point where you're going to take an open chip design and trying to make it into a product, you're going to need to ship it with some security expectations, right? Say out loud that we make no guarantees of anybody having physical access to this chip. That's a good start because people aren't going to have false assumptions about what your device does. People aren't going to buy your chip, put it into a device, and then sell it with that unwarranted security expectation. Now, let's say you do need to lock down some details. Let's say you want to implement some sort of secure boot or firmware protection or integrity checks, right? Use locks. When you do that, document them when and why you use them, right? So documenting when and why you use them, is helpful for the designer of the chip, as well as the person who's writing the documentation, who's telling users how to use this chip, right? And that's important because if you don't educate or encourage users to use those lock bits, they don't happen. So an ASIC example, this is from an XP datasheet. This is a chip that I encountered on a PLC that I was taking apart, programmable logic controller. And the programmable logic controller had the JTAG pins visible and exposed from outside of the device. So you could walk by this PLC mounted on a DIN rack and walk up to it and pop something in that would touch those JTAG pins and talk to the device. Do you think the code readout protection, that the JTAG granularity setting was set? No, it wasn't set at all. They didn't expect it to be an issue. They didn't really understand it. Now, going back, they might reconsider that. They might say, oh, well, maybe we should disable JTAG once our device is provisioned. There's a good reason for that. We have some granularity. We have the CRP 1, 2, and 3 modes that we can set it to. And CRP 3 means no future factory testing can be performed on the device. When you're designing a hardware device with a chip, you read this and you say, oh, my warranty is void if I set this bit. So I'm never going to set that bit because I'm never going to be able to say, hey, NXP, you gave me some bad chips. Like, well, can we test them? Like, well, the CRP3 is blown. You can't actually test them. Like, oh, well, too bad. Out of luck, not a problem. So what we've got here is granularity. You don't want to have just one lock bit that locks your whole system. You want lock bits that are relevant to exactly what you want to lock down. So what do we have? We have a CWE. Insufficient granularity of address regions protected by register locks. Okay, so specifically address regions in this one, but in general, lock bits, right? If you want to lock down a range of values, come on, next slide. Here we go. Next. So we might have a bunch of lock bits, right? And then each of these lock bits, all 32 of these lock bits, each lock a specific region of memory, right? This might work out really well. This could be great. But in this case, each region is 4K, right? Well, if you don't want to lock 4K of memory, you only want to lock 1K of memory. Or, you need access to a specific 1K of memory, which means you can't lock the adjacent 1K regions, right? There might be a situation where this granularity isn't good enough. You might need 64 bits. You might need more. You might actually need less. It's a balancing act to get like the level of granularity that you need to lock things down, along with at least reduced complexity so users actually use those lock bits. So revisiting my recommendations, document your security expectations. Use locks when you do. Document when and why you use them, and educate your software users, the downstream everyone, when you should be using those locks. I do have a checklist that has been evolved over time, like our checklist. What locks to apply to which registers? Who can set the locks? When? Can the locks be unset and why? When are they cleared? Locks are in which power, clock, and reset domains, right? That configuration bit itself, what domain is it stored in? Like if you remove power to one portion of the chip, can you wipe your lock bits without resetting the part? Can your configuration be cleared without clearing the lock itself? If you want to go and test this, right, you write some test cases. You just basically try accessing the lock, try clearing a set lock, messing with the lock configurations, then go through permutations. You might have a series of lock bits. Make sure all those lock bits, the correct lock bit is used on right target. And if you have combinations, like if you set all but one of the lock bits, does it have effect on how the others work? Yes, you can go and look at the code to figure out how all this code, the Verilog, the HDL, the gateware, to see how this all works. But it never hurts to go and try it on hardware as well to make sure it matches. So that's what we've got for you. To summarize, we basically got n ways to flip bits and n-1 ways to stop it. You can tell that I've got fewer ways to stop it because that's my approach. I'm looking to break stuff as opposed to your approach, which is probably trying to build stuff. You'd much rather have the n+1 ways to flip bits and the n ways to flip bits and the n+1 ways to stop it. So perhaps there's some research there and room for future opportunities.